In this video, I would like to discuss floating point data types in C and C++, and this is our handout. Integers are stored precisely, and if the size of an integer is larger than the actual data type can accommodate, an error may occur, or the compiler may not even be able to tell you. So that's what we call an overflow. A quick example: if I create a character char C and initialize it with the number 1, 2, 3, 4, 5, 6, 7, 8, 9, something big like this, way outside of the range of the character, if I try save it and build it, what I get from the compiler here is a warning that tells me initializing truncation from integer to character. Okay. And this is a very serious warning, because basically all the bits that represent the higher portion of this number will be dropped. Those will be truncated, and some kind of remaining garbage will be used to initialize our character. So this is obviously something that we always have to pay very serious attention to. And if we are working with numbers that have fractional components, then we switch over to using floating point numbers. For example, we can change this to float pi equals and use some level of precision. For floating point numbers, if the number of significant digits is larger than the number of bits available to store the number, then the number is simply rounded. So first of all, what is significant digit? Like, all these digits that we try to use are significant digits. And if our hardware, or the data type that we use for the floating point type on our hardware, is limited only to this level of precision, what happens is that this portion will be rounded. And so this will become 3.14. Of course, if our precision level is sort of like this, then it will be rounded to 3.146, like this, right? So this is really significant difference between the storage of the integer or any integral data type compared to a floating point, where all of a sudden we have this rounding approach to store this fraction in memory. In addition to this, even if our hardware is able to accept this level of precision, and our floating point data type can take this level, it still may not be able to store this exactly the way we specified it when we initialize it. So that's really fascinating. So there may be some extra precision or a loss of precision, and all errors referred to rounding are called round-off errors. So let's take a look at an example of round-off error. And before we continue, I also want to make a little correction here, that if we're using floating data type, then we have to use a suffix f, because without suffix f, this literal fractional number is accepted by the compiler as a double. Okay, so let's try this. We create a variable named sum, and we initialize it with 0. And we create a loop like this. And basically what I do here is that we will iterate 100 times. And 100 times we'll just say sum equals sum plus 0.1. So this will be similar to taking a long spreadsheet of data with a column with these types of values there, and everywhere we have 0.1, and we're just adding 100 rows together, and we would like to see what the sum is. And if we are accumulating 0.1 100 times, it's sort of like 0.1 multiplied by 100, which is a 10. So we can try to print something like this and say if our sum is 10, which is what we're expecting, we can say we have a 10. Otherwise, we say we don't have a 10. So let's save this and build this and run it, and look, it says we don't have a 10. Okay, then let's print this sum and just see what's the result of this loop. So we can print it like this. I'm going to switch to fixed notation, which is simply supposed to show all digits after the floating point. And I'm also going to use this maximum precision available with doubles, which will guarantee that we will be printing all of the digits stored in our sum. Okay, so let's build this again. And before we build, to include these manipulators here, I need another header, IOmanip. So I save this and we build again. Alright, so we run it, and so this is what it prints. It's basically, you can see that we get this little strange looking result, because 0.1 fraction cannot be stored in floating point data type exactly. It can be only stored with a certain level of precision. So in this handout, in our demonstration here, we will find out what this internally looks like inside the floating point data type as a data structure in computer memory. Floating point numbers are represented by what is called IEEE format, described by IEEE 754 floating point standard, which is designed to store floating point numbers of 32-bit size. So altogether, this is 32 bits. And this is known also as a single precision number. So single precision floating point number is 32 bits in size. And double precision floating point number is 64 bits in size. So the structure basically is a larger size for a double precision. And IEEE stands for Institute of Electrical and Electronics Engineers, and it's a professional association developing standards for computer science and electronic devices. And in our series of videos, we're going to explain how exactly these fractions are stored as bit patterns inside this data structure. So we should be able to explain how this is stored here, how this and this, how every fraction is converted to bits representing floating point data type.